Welcome to Echo 204, Study Session 7, Optimization, Maxima and Minima, an introduction to higher order derivatives. So far we have dealt with the first order derivatives. Now we'll turn to higher order derivatives. Given a function f of x, there are other derivatives which can be defined. This section discusses these higher order derivatives. Second derivative. The derivative f prime of x of the function fx is often referred to as the first derivative of the function. The adjective first is used to distinguish this derivative from other derivatives associated with the function. The second derivative function f prime prime of x, or d squared y by dx squared of a function, is a derivative of the first derivative. This is done by applying the same rules of differentiation as were used in finding the first derivative. Here are some examples. 1. Function f of x, first derivative f prime of x, second derivative f prime prime of x. Number 1, x to power 5. The first derivative will be 5x to power 4, and the second derivative will be 20x to power 3. Number 2, the function x to power 3 minus 2x squared plus 5x. First derivative will give us 3x squared minus 4x plus 5. Second derivative will give us 6x minus 4. Third function, x to power 3 over 2. The first derivative will give us 3 over 2 x to power half, and the second derivative will give us 3 over 4 x to power minus half. The fourth function, 2x minus 10 in bracket to power 3. The first derivative will give us 6 of 2x minus 10 to power 2, and the second derivative will give us 4x squared minus 240 to power 3. Remember, this is the power function. F of x equals u of x in bracket to power n. F prime of x equals n of u of x in bracket to power n minus 1 times u prime of x. F of x equals 3 of 2x minus 10 in bracket to power 3 minus 1 times 2. F of x equals 6 2x minus 10 all in bracket raised to power 2. To find f prime prime of x, differentiate the result in f prime of x. F prime prime of x equals 6 of 2 times 2x minus 10 in bracket times 2. F prime prime of x equals 12 2x minus 10 in bracket times 2. F prime prime of x equals 24 times 2x minus 10 in bracket. F prime prime of x equals 48x minus 240. Exercise. Find the first fourth derivative of the function x over 1 plus x where x is not equal to minus 1. Optimization. This involves maximizing or minimizing a function depending on the economic purpose it serves. 1. First order condition for optimization. For any function to reach its optimum point, the first derivative must be equal to 0. That is, f prime prime of x equals d square y divided by dx squared greater than 0. F prime of x equals dy by dx equals to 0. However, with the first order condition, we do not know the nature of the optimum point. The second order condition helps us to do this. Second order condition for optimization. The nature of the optimum point is determined by taking the second derivative. If the second derivative is negative, we have a maximum point. That is, f prime prime of x equals d squared y divided by dx squared less than 0. However, if the second derivative is positive, then we have a minimum point. Thus, f prime prime of x equals d squared y divided by dx squared greater than 0. Example 1. Find the relative extremum of the function y equals f prime of x equals 4x squared minus x and determine its nature. Solution. dy by dx equals 8x minus 1 equals 0. 8x equals 1. X equals 1 over 8. For the nature of the point, we differentiate again. D squared y divided by dx squared equals 8. Since the second derivative is positive, we conclude that this is a minimum point. Example 2. Find the relative extrema of the function y equals g of x equals x cubed minus 3x squared plus 2 and determine the nature of this point. Solution. dy by dx equals g prime of x equals 0. dy by dx equals 6x squared minus 6x equals 0. Solving the quadratic equation, we have 3x of x minus 2 in bracket equals 0. 3x equals 0 or x minus 2 equals 0. X equals 0 or x equals 2. The extrema occur at point x equals 0 and x equals 2. For their nature, we take the second derivative. D squared y divided by dx squared equals 6x minus 6. When x equals 0, 6 of 0 minus 6. D squared y divided by dx squared equals minus 6. Well, minus 6 is less than 0. When x equals 2, 6 of 2 minus x equals 12 minus 6. D squared y divided by dx squared equals 6, which is greater than 0. Application to revenue, cost, and profit. Revenue maximization. The money which flows into an organization, either from selling products or providing services, is referred to as revenue. The most fundamental way of computing total revenue from selling a product is total revenue equals price per unit times quantity sold. Example: the demand for the product of a firm varies with the price that the firm charges for the product. The firm estimates that annual total revenue is a function of price. R equals F of P, which equals minus 50p squared plus 500p. A. Determine the price which should be charged in order to maximize total revenue. B. What is the maximum value of annual total revenue? Solution. dr by dp equals f prime of x equals minus 100p plus 500. If we set f of p equals to 0, minus 100p plus 500 equals 0. Minus 100p equals minus 500, P equals 5. The sufficient condition should be tested. Thus, D squared R divided by dP squared equals f prime prime of x equals minus 100 less than 0. B. The maximum value of R is found by substituting P equals 5 into the function f of x. F of 5 equals minus 50 of 5 squared plus 500 of 5 minus 50 of 25 plus 2500, which equals minus 1250 plus 2500. Rm equals 1250, where Rm means marginal revenue. Cost minimization. Producers attempt to be efficient by minimizing costs. A retailer of motorized bicycles has examined cost data and has determined a cost function which expresses the annual cost of purchasing, owning, and maintaining inventory as a function of the size of each order it places for the bicycles. The cost function is C equals F. Example 1. A retailer of motorized bicycle has examined cost data and has determined a cost function which expresses the annual cost of purchasing, owning, and maintaining inventory as a function of the size of each order it places for the bicycles. The cost function is C equals F of Q equals 4,860 divided by Q plus 15Q plus 750,000. A. Determine the order size which minimizes annual inventory costs. B. What is the minimum annual inventory cost expected to be? Solution. We can rewrite the function as f of q equals 4,860 q to power minus 1 plus 15q plus 750,000. dc by dq equals f prime of q equals minus 4,860 q to power minus 2 plus 15. If we equate f prime of x equals 0, we have minus 4,860 q to power minus 2 plus 15 equals 0. Minus 4,860 q to power minus 2 equals minus 15. Minus 4,860 divided by q squared equals minus 15. Multiply both sides by q squared. Minus 4,860 equals minus 15q squared. Divide both sides by minus 15. 324 equals q squared. Take the square root of both sides. Square root of 324 equals square root of q squared. Q therefore equals plus or minus 18. The value equals minus 18 is meaningless in this application. We can check the nature of the critical point at q equals 18. D squared c over d q squared. I take that again. 1 2. D squared c divided by d q squared equals f prime prime of q equals 9,720 q to power minus 3, which equals 9,720 divided by q to power 3. Substitute q equals 18. 9,720 divided by 18 to the power 3 equals 1.667 greater than 0. B. To get the minimum inventory cost, we'll substitute 18 for Q in the original function. F of 18 equals 4,860 divided by 18 plus 15 of 18 plus 750,000, which equals 270 plus 270 plus 750,000, which gives us 750,540. Example 2. The total cost of producing Q units of a certain product is described by the function C equals 100,000 plus 1,500 Q plus 0.2 Q squared. Determine the number of units of Q that should be produced in order to minimize average cost per unit. B. Show that MC equals AC at the minimum point of AC. Solution. We are asked to minimize average cost and not total cost. So we need to find the average cost function from the total cost function. AC equals TC over Q. AC equals 100,000 over Q plus 1,500 plus 0.2 Q. AC equals 100,000 Q to the power minus 1 plus 1,500 plus 0.2 Q. dAC by dQ equals minus 100,000 Q to the power minus 2 plus 0.2. dAC by dQ equals 0 minus 100,000 divided by Q squared plus 0.2 equals 0. Minus 100,000 divided by Q squared equals minus 0.12. Multiply both sides by Q squared. Minus 100,000 equals 0.2 Q squared. Divide both sides by 0.2. Q squared equals minus 100,000 divided by minus 0.2, which equals 500,000. Take the square root of both sides. Q equals square root of 500,000. Q equals plus or minus 707.11. Negative quantity is not attainable, so we take Q equals 707.11. The nature of this critical point can be tested thus: d squared AC divided by dQ squared equals 200,000 Q to the power minus 3, which equals 200,000 divided by Q squared, which equals 200,000 divided by 707.11 to the power 3, which equals 0.00056 greater than 0. B. MC equals dTC divided by dQ, which equals 1,500 plus 0.4 Q. AC equals 100,000 divided by Q plus 1,500 plus 0.2 Q. Substitute the value of Q at which AC is minimum, that is 707.11, into both MC and AC function, and so MC equals 1,500 plus 0.4 of 707.11, which equals 1,782.84. AC equals 100,000 divided by 707.11 plus 1,500 plus 0.2 of 707.11, which gives us 1,782.84. It is shown that MC equals AC, which equals 1782.84 at the point where AC is minimum. Practice exercise. 1. A firm has determined that total revenue is a function of the price charged for its product. Specifically, the total revenue function is R equals F of P equals minus 10 P squared plus 1750p. A. Determine the price which results in the maximum total revenue. B. What is the maximum value of total revenue? 2. A community which is located in a resort area is trying to decide on the parking fee to charge at the town-owned beach. There are other beaches in the area and there is competition for bathers among different beaches. The town has determined the following function, which expresses the average number of cars per day, Q, as a function of the parking fee, P. Q equals 600 minus 12p. A. Determine the fee which should be charged to maximize daily beach revenue. B. What is the maximum beach revenue expected to be? C. How many cars are expected on an average day? The example below will be helpful in solving question 2. The demand function for a firm's product is Q equals 150,000 minus 75p. A. Determine the fee which should be charged to maximize daily beach revenue. B. What is the maximum beach revenue expected to be? C. How many cars are expected on an average day? TR equals 150,000 minus 7p in bracket times P. TR equals 150,000 minus 75p squared. To maximize, dTR by dP equals 0. dTR by dP equals 150,000 minus 150p equals 0. 150,000 equals 150p. P equals 150,000 over 150. P equals 1000. B. The maximum value of TR is obtained by substituting 1000 for P in the TR function. TR equals P times Q. TR equals 150,000 times 1000 minus 75 of 1000 square. TR equals 15 million minus 7,500,000. TR equals 7,500,000. C. Substitute 1000 for P in the demand function. Q equals 150,000 minus 75 of 1000. Q equals 150,000 minus 75,000. Q equals 75,000. This is the end of study session 7. Thanks for listening.